Welcome to Manufacturing Processes, Machining and Machine Tools lectures by Professor Joyjeet Ghose. This is the 13th lecture of a series of lectures. This lecture will be on milling machine and related aspects, part 2. He will be discussing about plain milling cutter nomenclature, milling processes like peripheral milling, face milling, end milling, up milling and down milling, cutting speed, feed, and depth of cut in milling processes, machining time calculations. Also several numerical on machining time calculation and MRR calculation of milling process is also discussed. So, do not miss and watch the full video. For the next video in the lecture series, please click the suggested video link above. You may also click on the playlist at end of the video to access all the videos. Please subscribe this channel and yes, do not forget to like and share. Also click on the bell icon to receive instant information of new videos uploaded. Thank you.
Hello friends, welcome to this lecture. This lecture is a continuation of the previous lecture. In this lecture we will be discussing about milling machines and mainly we will be discussing the plain milling cutter nomenclature, and we will be discussing about different types of milling processes, and also don't miss out, we will be discussing on discussing various types of numericals based on machining time calculations of milling processes. So let's start. We'll start with the nomenclature of or the geometry of a plain milling cutter. So one of the principal geometry of a plain milling cutter is the outside diameter. The outside diameter is the diameter, you can see this dotted line, diameter passing through the peripheral cutting edges. So this diameter is used for calculating the peripheral cutting speed. That is, when you calculate the cutting speed, V is equal to pi dn by 1000. That d is this d, that is the outside diameter. This is the diameter passing through the peripheral cutting edge, that is called the outside diameter. And the diameter or the diameter of the circle passing through the fillet, bottom of the fillet of the milling cutter is called the root diameter. So this diameter is called the root diameter. Diameter of the circle passing through the root is called the bottom of the root is called the root diameter, and diameter of the circle passing through the peripheral cutting edge is called the outside diameter. Okay, so now this part is called the tooth of a milling cutter. This part is called the tooth. This is the body, and the part from the body extending to the towards the peripheral cutting edge is called the tooth, and this is called the tooth face. This is the surface between the peripheral cutting edge and the fillet. So this is the surface between the peripheral cutting edge and the fillet, and this is the surface where the chip actually impinges on and slides. So as this is rotating in this direction, the chip will come and strike here and it will move in this direction. So this is the surface where it strikes. This surface is called the tooth face, and fillet is the bottom of the between the two teeth, which is radius, which is a radius is given. This radius is called the fillet. Now why this radius is given? So this radius is given so that chip can curl and can flow easily. That's why this radius is given. This is called the fillet. And the portion extending beyond the peripheral cutting edge, this is called the land. This is called the land. This is called the land of the milling cutter. The land is slightly relieved so that to avoid any kind of interference or to reduce the interference, the land is slightly relieved. So there is a relief angle here. So this is the relief, and this is the gas angle. Gas angle is the, you can see here, this is the gas angle. The gas angle is the angle between the face of the teeth and the back of the corresponding teeth, back of a corresponding teeth that follows this particular teeth. Okay, so this is the gas angle. The gap between the two teeth are called the float. This gap is created by the clearance angles. This gap is created by the clearance angle, and it provides the space for the chips to flow. Okay, this is the land. With this we move on the angles. Okay, one of the primary angle is called the rake angle. The rake angle is the angle between the face, this is the face, and the radius of the cutter measured in a plane perpendicular to the axis of the cutter. This is the rake angle. This is the rake angle. Then we have relief angle. The land is slightly relief to avoid the interference. This is called the relief angle. And we have the clearance angle. The clearance angle is given so as to produce the space between the teeth and to create space for the chips to flow. This is the relief angle. And then we have the leap angle. This is the leap angle between the land and the face is called the leap angle. And we have the helix angle. Helix angle is measured as a tangent to the peripheral cutting edge and the axis and the plane containing the axis. This angle is called the helix angle. This angle is called the helix angle. When you look radially, at the point of intersection of the axis and the tangent is called the helix angle. These are the geometry of a plain milling cutter. With this, we move on to the various types of milling operations. So milling operations you can classify into three categories, basically: slab milling, face milling, and end milling. So in slab milling, we use basically a peripheral milling cutter, where the width of the peripheral milling cutter extends beyond the width of the workpiece which you are cutting. That is called a slab milling, and the surface that is generated is a flat surface parallel to the axis or parallel to the rotation of the axis of the cutter. And here milling machine which also generate a flat surface, and face milling we also generate flat surface using a wide diameter milling cutter which is rotated perpendicular to the surface that is generated. And this is also rotated perpendicular to the surface generated, but it is smaller in diameter and mainly used for various operations like cutting slots, making pockets like this, or making a profile. Such type of operations, end milling operations, are normally done. So peripheral milling already I have discussed. Now peripheral milling can be of two types: up milling or conventional milling, or down milling or climb milling. So what happens in up milling? The cutter is rotating in this direction and this is fed in this direction. So it is against the direction. The feeding is against the direction of rotation. So what happens? The chip is thin at the start and thick at the end. The cutting force is less at the start and cutting force is maximum at this end. And what it is happening is here it tries to lift the workpiece. Therefore, more clamping force is required to hold the workpiece in up milling or conventional milling. Okay, so this is the measure. This is normally used in conventional milling machines. Whereas, and you can see a wavy surface. By the time it comes, next teeth is engaged, it moves slightly ahead. Therefore, we have a wavy surface here. Okay, in down milling or climb milling, the chip starts out thick at the start and leaves out thin at the end. Similarly, the force is maximum at the start and minimum at the end, and it tries to drag. Now, for this, you don't require a much clamping force because it is applying a force downward direction. So clamping force is less. However, it tends to drag and pull the workpiece forward, and it may damage the workpiece if your table screw is not very rigid. Therefore, it is normally used in CNC machines and not in conventional milling machines. So this is down milling. A very often asked in the exam: differences between up milling and down milling. Okay, this is face milling operations. Already I have discussed. Okay, the different types of operations, peripheral milling operations, are slab milling operations, where the cutter extends beyond the work is on both sides. It generates a flat surface, and the axis of rotation of the cutter is parallel to the surface that is generated. And we have side milling operations, where we use a side milling cutter. This is a side milling cutter for cutting slot, and here we are using a side milling cutter for cutting shoulders like this. I told you during the discussing the side milling cutter, this is a half side milling cutter. Both are half side milling cutter. It has cutting edge on this side and this side, and this has cutting edge on this side and on this side. So it's generating a this side sort of surface. And this particular, when we use two half side milling cutter in combination to produce this type of shoulders, we call it straddle milling operation. And we have angular milling operations, where we use angular milling cutter. This is straddle milling operations. This is form milling operations using a form milling cutter. And this is slitting operations, where we parting the workpiece into two parts and we are cutting a slot at an angle. This is also done by the same slitting saws. And form milling operations by form milling cutters, corner rounding, gear milling, all are called form milling. And straddle milling already I have discussed. And we have gang milling. In gang milling, more than two cutters are engaged simultaneously for generating a surface. So here three cutters are being used. In fact, yes, three cutters are being used. For 1, 2, 3, 4, 5. 5 milling cutters are used. Okay, two half side milling cutters and 3 plain milling cutters are used. So here 5 milling cutters are used simultaneously, and then for this is called a gang milling operations. And phase milling operations, we have discussed the peripheral milling operations, and these are phase milling operations where the axis of rotation of the cutter are perpendicular to the surface being generated. So you have conventional phase milling, we have end millings of various types. End milling can be pocket milling, you have pocket profile milling, pocket milling, and surface contouring. Various types of operations can be performed. So these are different types of milling operations. With this we move on to the cutting parameters, that is the cutting speed, feed and depth of cut. The cutting speed is same as that of any other machine tools. Here it is the peripheral cutting speed with which the cutter is being rotated, where d is the outside diameter of the cutter and v is equal to pi d in mm and v is equal to pi dn by 1000 in meter per minute. And feed are of three types here. Feed per tooth. Feed is basically defined as the distance advanced per tooth, per engagement of the tooth. So it is the distance advanced by the workpiece when by the time the next tool is engaged. So that is called the feed per tooth. And if you want to find out the feed given per revolutions, then you have to multiply fz into z, where z is the number of teeth of the cutter around the periphery. So fr is equal to fz into z. And feet per minute, that means if you want to find out the feet velocity, then it will be fz into z into n, where n is the rpm. So, and depth of cut is obviously the depth up to which you are cutting is called the depth of cut. And the machining time obviously will be the time taken for machining by the L. L is the length of machining, and this is the velocity in the feed direction, that is the fz into z into n. This will give us the machining time. Now what is this L? L will vary from operation to operation, or from process to process. For slab milling operations, it will be L is equal to L plus LA. L is the length of the job and LA is the approach length. Whereas for face milling, it will be L length of job plus LA plus LO, over travel. There will be over travel. So how that we'll see. So here this is slab milling operations where this operation is taking place. This is a peripheral milling. This is rotating and this is fed in this direction. So here it is removing the workpiece. Now where from should you start? You have to start from here so that it touches this corner, and you rotating it. As you are rotating it, it will be cutting in this direction. Okay, it will be cutting in this direction, and when you finish it, when this point reaches this point, it will be finished. So therefore there is no over travel, and this is the minimum distance. Of course you can start from here, you can and end here, that doesn't matter. This what I am calculating is the minimum approach length. This should be the minimum approach length so that the entire section is cut properly. So what is this LA? Now if this is the depth up to which you are cutting, so this portion will be this portion. This is your d by 2. If this is d by 2 and this is your d, so this is d by 2 minus d will be this portion. So I am interested in finding out this length. So this is the hypotenuse. So this length will be root over square of the hypotenuse minus square of this length. So d by 2 whole square minus d by 2 minus d whole square. So this gives us LA is equal to root over small d minus capital D minus small d. Okay. So this is the for slab milling. But in case of face milling, this is slab milling. You can see this is the depth of cut. The cutter is rotating and it is crossing. So you have to start from here and you have to finish it here. Okay. So this is for face milling. Now face milling again can be two types. If the diameter of the is quite large enough to take the entire cut in one entire width in one cut, then is case difference. And if you want to remove by different number of passes, then the case is different. So here, if when the width of the card is greater than d by 2, then we'll start from here so that the entire workpiece is completed and end here. So there is, sorry, start from here and end here. Of course you can start from here and you can end here, but this is the minimum distance you have to traverse. So there is an approach length and there is a over travel, and that is equal to d by 2. That is equal to d by 2 because this distance is d by 2. So that is d by 2. That is d by 2. Whereas here in this type of process, here you will remove, and w is the width of the cut. W is the width of the cut, not the workpiece. So here w is the width of the cut, and this is less than the d by 2. So number of passes is required. How many passes is required? If this is b, so b divided by w will give you the number of passes required. So in this case, you start from here and you end here, and that distance, just like previous case, we have found out this will be equal to LA is equal to LO is equal to root over w into d minus w. So this is the case for face milling where w is less than d by 2. So with this knowledge, we should be able to solve some numericals based on this. Let's see. This is the again another figure of the same thing. And material removal rate. Material removal rate is defined as the length into width into where w is the width of the workpiece and d is the depth of the cut and divided by the machining time t. So this will be mm cube by per minute. Okay, so this is the problem. Just take a time and go through this problem. Pause the video here and go through this problem carefully. So here there is a certain material, and in that certain material which is of dimension 100 into 250 mm. So length is 250 and breadth is 100, is to be produced on a horizontal axis milling machine. So therefore you have to use a slab milling operations, and an HSS slab mill is used of 100 mm diameter and 150 mm width. Now entire thing has to be cut in one depth of cut, that is 2 mm, and the cutter has 8 teeth. And for this material, if you check the handbook, you will find that the cutting speed should be 20 meter per minute and the feet should be 0.13 mm per tooth. However, it is given in the question, so you don't have to worry about the material. It is given in the question. Okay, fine. Now here the diameter, the width of the cutter is 150 mm. The width of the cutter is 150 mm. So therefore it can remove the material, entire material in one depth of cut of 2 mm. For that, the width we have to take is 100 and length we have to take it as 250 mm. That you should remember. That you should remember. So that basically means here if this is the width, this is 100 and this is 250, we have a cutter which is 100 mm in diameter and 155 in width. So it has cutting edges like this. So therefore this should be the width, and we have to remove in a single cut. So this should be the width and this should be the length, and this is slab milling, so we have to find out the approach length, which will be root over d minus. Okay, so let's see. This is the case. This is the 2 mm. This 2 mm has to be removed. Okay, and approach length we have to find out. So first we have to find out the spindle speed. The spindle speed v is equal to pi dn by 1000. So n will be equal to 1000 v by pi d. So from that we find out 63.6 is rpm, which I have taken it as 65 rpm. Okay, now a question may arise, why you have taken it as 65 rpm. Okay, to explain this from practical point of view, when you calculate the spindle speed from the recommended cutting speed, that spindle speed may be in fraction. Now that fractional spindle speed may not be available in the machine. Okay, may not be available. Why it will not be available? Fractional spindle speeds are not available in machines. So therefore we will select a spindle speed which is near to the one calculated and which is available in the machine. Let's say if you have calculated 63.66 and the machine it is available 100 mm nearest to one, so we will be selecting a 100 mm spindle speed. Okay, so that is the practical approach of solving this type of problem. However, Let's take a round figure here. I have taken a 65. You are free to keep it as 63.66 mm. It is up to you, but from practical point of view, we take the spindle speed which is nearest to the one available in the machine. So the entire stock has to be removed in one pass. So therefore, we have to take 100 mm as the width and 250 mm length, 250 mm as the length. Okay, so we calculate the LA comes out to be this. The small d is 2, that is the depth of cut, that comes out to 14 mm. So LA is 250 plus 14 is 264. Again, it is coming out to be, and FZ is given as 0.13, Z is 8 number of teeth, and 65 I have calculated. You can keep it 63.6, is up to you. You should get a figure around this 3.9.05 minutes. Now while calculating the material removal rate, you can take L as 250 or you can keep it as 264. It's up to you. The answer will be near to this. It will not affect much. And width is given as 100 and depth is 2, and the time is taken. We have calculated here 3.905. So this gives us 13,521.13 meter cube per minute of material removed in unit minutes. That's it in the first problem. Let's discuss the second one. At this point of time, just pause the video and try to solve it yourself. Let's see if you can solve it. Okay, so a surface of 115 mm wide, so here it is clearly mentioned 115 mm wide and 250 mm long, is to be rough milled with a depth of cut of 6 mm. So here D is 6 mm and Z is 16 and D is 150. D is 150 and the work material is given as an alloy steel whose Brindle Hurdles number is 200. From that we can calculate, we can find it out from the handbooks, the cutting speed required and the feed. So that is given in this question. We don't have to worry about that. Where cutting speed is 60 meter per minute and feed is 0.18 mm per tooth. So what we have to do? We have to do face milling operations, and the width of the cut is how much? 115. So can we remove 115 with a face mill of diameter 150? Yes, we can. And W is greater than D by 2. So therefore LA is equal to L naught is equal to D by 2, that is 150 by 2, that gives 75 mm. And similarly to the previous problem, we have to calculate the spindle speed. Spindle speed comes out to be 127.32. I have taken it as 125. You can keep it as this, or you can keep it as 150, or you can take it as 100. Is up to you. Let's take it as 125. If I take it as 125, so machining time L will be 250 plus LA is 75 plus L naught is 75. So that gives us 400. So 400 by FZ is 0.18 and number of teeth is 16 and the RPM we have calculated as to be 125. This gives us 1.11 minute. Let's solve one more problem. So in this problem, again pause this video here and try to solve it yourself. If you are not able to solve, then you can see the solutions or you can check your solutions with mine. Okay, so here you have to determine the time required to mill a 125 mm long keyway using an HSS end mill of 20 mm diameter having a 4 teeth. Depth of key is to be 4.5 mm and feet per tooth is to be taken as 0.1 mm and the cutting speed is to be taken as 90 meter per minute. Okay, so here if I draw the figure, it is something like that. So this slot has to be cut using this 20 mm diameter end mill. So here there will be only LA, because once this cutter reaches here, the job will be completed. You don't have to over travel here. You are cutting a slot. So what is the minimum distance? The minimum distance will be the radial distance, the radial distance, that is D by 2 from here. That is the minimum distance. You can start from much more distance, that is not an issue, but the minimum distance would be D by 2. So LS would be D by 2. So the entire length should be 125 plus 20 by 2, that is 10. So L should be, capital L should be 135 mm. So with this knowledge, You can find out n, and n is coming out to be around 1400 something. Let us take it as 1500 rpm, and you can keep it as this, no issue. So approach length is this, so over travel is 0, so this comes out to be 0.225 minutes. So I hope this is clear to you. So with this we come to the end of this lecture. If you have any doubt, please feel free to put it in the comment section, or you can contact me through email. Thank you for watching this video.